Welcome to this educational video where we'll explore a fascinating analogy between two seemingly different areas of physics, plasma physics and quantum chromodynamics, or QCD for short. Both of these fields deal with energy thresholds that give rise to observable phenomena, and understanding the parallels between them can provide valuable insights into fundamental physics. Let's start with an overview of our analogy. On one side, we have plasma physics, which studies ionized gases where electrons are separated from their nuclei. On the other side, we have quantum chromodynamics, which describes the strong nuclear force and how quarks and gluons interact to form particles like protons and neutrons. In both cases, we observe discrete energy thresholds that must be crossed for certain phenomena to occur. Let's dive deeper into each side of this analogy to understand the similarities. First, let's explore plasma physics and atomic energy levels. Hydrogen plasma is one of the simplest examples. When hydrogen atoms are ionized, we have a mix of protons and electrons. When these electrons recombine with protons, they transition between different energy levels in the hydrogen atom. These energy levels are quantized, which means electrons can only exist at specific discrete energy states, labeled by quantum numbers like n equals 1, 2, 3, and so on. The energy of these levels is given by the formula E sub n equals negative 13.6 electron volts divided by n squared, where n is the principal quantum number. When electrons transition from a higher energy level to a lower one, they release energy in the form of photons. The energy of these photons is exactly equal to the energy difference between the two levels. This gives rise to spectral lines like the Lyman series or the Balmer series. For example, the Lyman alpha line corresponds to a transition from the n equals 2 state to the n equals 1 ground state, which requires an energy of 10.2 electron volts. This is a threshold energy. Below this value, we simply cannot observe the Lyman alpha spectral line. Now, let's turn to quantum chromodynamics, or QCD. QCD describes the strong nuclear force, which is responsible for binding quarks together to form hadrons, like protons and neutrons. Unlike the electromagnetic force, which is carried by photons, the strong force is carried by particles called gluons. In QCD, both quarks and gluons carry a type of charge called color, though it has nothing to do with visual color. One of the most interesting aspects of QCD is that neither quarks nor gluons can exist as free particles. They must be confined within composite particles. In the QCD Lagrangian, which describes the fundamental equations of the theory, gluons are massless particles. However, something remarkable happens due to the strong interactions and nonlinear nature of QCD. A mass gap emerges. The mass gap is the minimum energy needed to create the lightest possible bound state in the theory. No matter how little energy you put in, you can't create particles with arbitrarily small masses. There's a threshold that must be exceeded. This is fundamentally different from quantum electrodynamics, where photons can have arbitrarily low energies. Now, let's explore the core analogy between plasma physics and QCD. In hydrogen plasma, electronic transitions only occur when the excitation energy exceeds a certain energy threshold, delta E. For example, the Lyman alpha transition requires exactly 10.2 electron volts. Similarly, in QCD, bound states of quarks and gluons can only form when enough energy is available to overcome the mass gap, delta M. The lightest known meson, the pion, has a mass of around 140 MeV/c squared. In both cases, we're looking at a minimum energy threshold that must be exceeded for a new observable phenomenon to occur. In plasma, this observable is the emission of a photon at a specific wavelength. In QCD, it's the formation of a hadron or glue ball with at least the minimum mass. Despite the vastly different energy scales and underlying physics, the conceptual structure is remarkably similar. Let's conclude by discussing some applications and implications of this analogy. Understanding the parallels between plasma spectroscopy and QCD could inspire new experimental approaches. For example, high-resolution plasma diagnostic techniques might suggest new ways to probe the hadronic mass spectrum. Threshold scan techniques used in plasma physics could be adapted for experiments at particle accelerators to better understand the QCD mass gap. This cross-disciplinary perspective highlights how quantized energy gaps give rise to structure across vastly different physical scales. From atomic energy levels to hadron masses, the emergence of discrete structures from continuous underlying theories is a profound feature of quantum physics. The QCD mass gap remains an open problem in theoretical physics. In fact, providing a rigorous mathematical proof of its existence is one of the Clay Mathematics Institute's $1 million Millennium Prize problems. By drawing connections between well-established areas of physics like plasma spectroscopy and frontier areas like QCD, we may gain new insights into some of physics' most challenging problems. To summarize what we've learned today, both plasma physics and quantum chromodynamics feature energy thresholds that must be exceeded for observable phenomena to occur. In plasma, these thresholds correspond to the discrete energy differences between atomic levels, leading to spectral lines. In QCD, the mass gap ensures that all observable particles have a minimum mass, despite the massless nature of gluons in the theory. This analogy suggests that techniques from one field might be adapted to provide insights in the other. The existence of these energy thresholds reflects a fundamental characteristic of quantum systems: the emergence of discrete structures from continuous theories. Thank you for watching this exploration of energy thresholds in physics.